I know, but it's so nervous. It's super funny too. Like I did a speech.
Okay, so let's see.
And I ended up getting third in it, and it was in front of like 100 plus people. And I still get nervous. Like 20 do we have a signing machine?
I'll get you. Just sorry, give me just 1 second. Stop.
I'm excited.
Oh, it's no, I don't.
Brian, you're gonna have some editing to do.
No idea. Yeah. Yeah, would you make that students?
Anyone up for it too? For students, if you guys want to come and sign by your name to get your extra credit.
Wait a second, I'm trying to figure out how to turn off the speakers here. Hang on 1 second. I don't have any control over mic back here. I think so.
It's funny, I was supposed to go these like those
Turn it off. Okay, Sonny, can you hear me? You can't hear me now because I turned off the mic.
actually
Sonny, can you hear me right now?
Yeah, I can hear you.
We can all go together.
Yes. There's some serious feedback going on.
Okay, is that better?
Yes.
Okay. Okay, so we were playing the audio from the YouTube live feed that we're playing right now.
Yeah, don't do that. I've been doing live Google Hangouts for 3.5 years now, and
Yes, good, very good. Okay, all right. Now I think we're okay.
That music was cool.
That's how people identify Boise State. Just both guys.
Do you need me to do anything else, Brian?
No, have a seat. Hey, well, welcome everybody. This is a real treat. We're going to have a real fun presentation from an actual rocket scientist who actually for real works with NASA. Before we get to that, let me introduce myself. I'm Brian Jackson. I'm a professor here in the physics department. I teach astronomy. Several of my students are in the audience. And for those of you who have not signed in, please do. This is extra credit. So I'm sorry if you're not in the class, you can't get any extra credit.
Life extra credit. Yeah, right.
So we have a real fun evening for you plans. We're going to do a presentation tonight about the OSIRIS-REx mission. We'll take some questions, and then we'll go out under the stars and do some stargazing on the top of the Brady Street Garage. Hopefully it's still clear. Did everyone see the weather on the way in? Did it look like it was still clear outside? Okay, good. It's been up and down all day, you know. Okay, before we do all of that, we have a special announcement from one of our students here. So let her come on up. I have your video queued up here, Anne, by the way.
Sorry if you want to
Oh,
play
wait,
it.
I'm not in it. Okay. I was stressing
It's
out.
just like you guys was. Why was it work?
Do you want to do this or do you want to?
How about play the video so that, because that'll go through stuff faster
Sure.
than I probably will.
Hey guys, my name's Anna.
Sorry, it's not going to be loud.
Lights.
And with your help, we would love to go to this cause. This PhysicCon is a quadrennial physics congress that is held only once every 4 years.
And we'll have opportunities to go to such places as Toulouse,
Or the SLAC, Particle Accelerator Laboratory.
or even NASA Ames Research Laboratory. All of these experiences will blow our mind. And hopefully with your help, we can go too.
It's God.
Oh, my God.
Should be a music cue.
Yeah, seriously, what happened to,
Yeah.
what happened to Johnny and the Jets there?
Yeah,
Yeah, we don't have right that song.
So basically, we're running a crowdfunding campaign in order to be able to go to PhysCon for 12 of us. We already reached our initial goal of $2,500, and we are currently at $3,600. But in order to fully fund our transportation, hotel, and our registration, we need $6,000. So we have approximately $2,500 to go. So if you guys are able to donate literally even $5, or even just simply share it on your Facebooks or share it with your family, anybody who you think might be able to donate, that would be awesome. And the URL is up there. It's ponyup.boisestate.edu/nerdkingdom. And if you guys have any questions, please let me know, and I will answer them for you.
Yeah, thanks, Hannah. Yeah, so please help support our students. They really need to get out of Boise.
We don't get out much. We're nerds.
Okay, let me introduce tonight's speaker. Let's see, where did she go? Sonia, you're still there, right?
I'm still here.
Perfect. Okay. So it's a real pleasure tonight to introduce Alessandra Springman. She's currently a graduate student at my alma mater, University of Arizona, in the Lunar and Planetary Labs. Before that, she was an undergraduate at, a master's student at MIT, where she worked with a friend of mine, Lindy Elkins-Tanton, and Rick Benzel on the terrestrial magma ocean solidification. And before that, she got her bachelor's degree in astrophysics from Wellesley in Massachusetts. Sandy has done a variety of different things, including currently working with the OSIRIS-REx asteroid sample return mission, and she'll tell us all about that this evening. Let me flip it over to her. Sandy, I'm going to put you on the screen for just a second so you can wave at everybody, okay? There we go.
I'm from Tucson. It was 90-something degrees today. I wish you were here.
Okay, let me know. Should I flip you to your presentation?
Yeah, if you want to flip over to my slides, we can get started.
Everyone wave? You guys want to wave?
Hey! Hi, audience. Hello, Boise.
All right. Here we go. Take it away.
All right, so can everyone see my slides? Can everyone see the spacecraft?
Yes.
Okay, great. All right, so I'm Alessandra Springman. Most people call me Sandy, and I'm going to be talking about the OSIRIS-REx mission tonight, which is a NASA mission that's going to an asteroid, and it's going to bring back a sample of it. If you have any questions during the talk, feel free to raise your hand. I might not be able to see you if you're too far on the left or on the right. And we'll have plenty of time for questions at the end. So with that, let's get going. So why do we study asteroids? Does anyone want to venture a guess as to why we study asteroids? Brian, I'm going to make your students work for this using the microphone. Any answers?
We got someone in the front here.
Okay.
Asteroids have a composition similar to the bulk composition of the Earth, so we can learn about our planet by studying asteroids.
Yeah, so we can learn about our planet by studying asteroids. That's a great reason. Anyone else want to venture a reason as to why we study asteroids?
Potentially the source of life on Earth.
Yeah, they could have been the source of life on Earth. Earth got all of its water from asteroids. It could have gotten amino acids. It could have gotten organics from asteroids. Any other reasons why we study asteroids?
They have a potential for mining precious elements that are scarce around the Earth.
mining asteroids, using them for resources. Those are all really good reasons to study asteroids. So if you're not familiar with what an asteroid is or where an asteroid is, we'll be talking about that in just the next couple of minutes. So why asteroids? So asteroids hang out in the main asteroid belt. So here we have the solar system. We have the sun at the center. We've got Mercury, Venus, Earth, and Mars. Mars and Jupiter, we have asteroids. And we think there are at least about 500,000. If you can move the microphone away from the speakers, we might get less feedback. We think there are about 500,000 asteroids out there right now. There's we know of hundreds of thousands, and we haven't quite discovered all of them yet, but we know there are more out there. And so here's just another schematic of the solar system. You have the sun in the center. You have this belt of asteroids. They're leftovers from planet formation. They were the little planet that couldn't. And so asteroids range from Ceres, which is about the size of Texas, down to smaller, to the sizes of grains of dust. And at that point, they're not really asteroids. Maybe they're meteoroids at that point. And in the rest of the solar system, we have Jupiter, Saturn, Uranus, Neptune. We have the Kuiper Belt, which is full of a bunch of objects like Pluto, Eris, big cold things. And we're not going to really be talking about those tonight. We're not going to be talking about comets. We're really going to be talking about the small rocks that are Texas-sized and smaller that hang out in between Mars and Jupiter, and then also sometimes come by Earth. So sometimes when we think about asteroids, we think about Star Wars, we think about The Empire Strikes Back, and we think about that scene where the Millennium Falcon was flying through the asteroid belt, where this asteroid field. And we think, oh gosh, the asteroids are really close together, they must be really dangerous, they must be bonking into each other all the time, and there must be full of these giant space worms that somehow don't need oxygen to survive. Unfortunately, the people at Lucasfilm are much more interested in telling stories than they are on providing good science. But the asteroid belt is not like the asteroid field that you see in The Empire Strikes Back. The spacing between asteroids is thousands and thousands of kilometers, thousands of miles between them. You wouldn't even be able to see one asteroid from another, pretty much, if you were on the surface of an asteroid, unless you had a telescope. So here is an animation of the solar system of all the asteroids we know of. And so this is a little bit confusing if you're not an astronomer, so I'll try to orient you to it. So in the very center, this little yellow star, that's the sun. This big circle is the orbit of Jupiter. The little circles are Mars, Earth, Venus, and Mercury. And each little green dot is an asteroid. And so as in 2003, we didn't know where about as many asteroids as we do now. And even though this looks really dense, they're so far apart in reality. So the green dots are asteroids in the asteroid belt. They're the well-behaved asteroids that tend to go in pretty circular orbits, and they stay between Mars and Jupiter. However, there are also some bad asteroids, and they're called near-Earth asteroids, and they're these ones in red. They're these little red dots. And they pass almost as close as the Earth passes to the sun, and sometimes they pass really close to Earth. So we call them NEOs, near-Earth asteroids, or NEOs, near-Earth objects, NEAs, NEOs, near-Earth asteroids, near-Earth objects. Sometimes they're near-Earth comets in this population, and they all came from the asteroid belt. So they all originated as asteroids in this region between Mars and Jupiter, and for whatever reasons, maybe they were hit by something, maybe sunlight affected their orbit, they were kicked into the inner solar system, which is what we call this region sort of between Mars and the sun, and they pass by Earth. And when they're potentially hazardous, when they pass really close to Earth, we call them potentially hazardous asteroids, or PHAs. So it's in our best interest to study these things, because what if they come hit us someday? So what if they come hit us someday? Who's been to northern Arizona and seen Meteor Crater? I know Brian has probably been there. In northern Arizona, there's a huge hole in the ground. It's about 3/4 of a mile across, and it was formed tens of thousands of years ago when an asteroid exploded over northern Arizona. This whole thing, again, 3/4 of a mile across, and it was created in 10 seconds. So often when we think about impacts here on Earth, we think about, oh, these giant fireballs, or this is going to kill all humans or all the dinosaurs, but also it's important to think about what happens on Earth. Pretty much any mammal in northern Arizona, when this hit, was instantly killed. It was a very bad day to be alive when this thing hit. So that's another, and then mostly when we think about asteroid impacts, we think about images like this, but these are really, this sort of visualization, this painting is super unrealistic, because any asteroid that big, it's in the asteroid belt, it's not going to come hit Earth. It doesn't pose a threat to this planet. So when we see images like this, it doesn't really help us think, but if you can start thinking about what happens when these asteroids actually do hit and what effects they have on their ground, this is a little more realistic. And you can even see the layers in the rock in the northern Arizona desert. You can see the various layers of sandstone and limestone that this meteorite vaporized. So when we're also talking about meteorites, meteorites are pieces of asteroid that come through our atmosphere and they hit the ground. And so meteorites are really cool because it's a way to study material from space without having to go to space. So meteorites are messengers from other worlds, and they tell us about other asteroids, and they tell us even about other planets. So we have a couple of meteorites here. This one is an unheated meteorite. I'll talk a little bit about that later, but we think these unheated meteorites have remained pretty much unchanged for 4.6 billion years, since the solar system formed 4.6 billion years ago. And they contain little grains of material that just haven't been heated. They haven't, for whatever reason, they haven't melted out there in the solar system. They've been preserved in their pristine state. We also get meteorites from other planets. We get these Martian meteorites, which are really cool. And we know they're from Mars because there's trapped gases in these meteorites. And the composition of these trapped gases, it's argon, it's various Nobel gases, it matches the trapped gases that the Viking landers measured on Mars in decades ago. So that's really cool that we can confirm that this material comes from another world, from spacecraft we've sent to Mars, and that we can study processes on Mars by these samples that have landed on Earth. We also get these really beautiful meteorites. They're called pallasites. And so what they are is they're iron and nickel, and they surround these olivine crystals, or dunite if you're into gems, or peridotite. You get these beautiful yellow and green gems mixed in with this iron and nickel. And so if you slice them really thin and hold them up to the light, you get these really sort of cool stained glass effects. And the reason this looks blue is it's just reflecting the sky. And then finally, you get these iron meteorites. Iron meteorites are really cool because they come from the cores of failed asteroids. So an asteroid had formed from material that looked a lot like this, and then it melted. And so all the iron in the asteroid sank to the center, forming a core, and all the lighter rocky minerals rose to the top. And so you get an iron core and a rocky mantle, just like our Earth. But for whatever reason, this asteroid, unlike our Earth, got blasted apart, and the core broke apart, and it gets delivered to Earth. And these lines that we see in these iron meteorites, they're called Widmanstätten lines. The bigger they are, the slower the asteroid it came from cooled. So that means that big lines mean you had a big asteroid, and small lines mean you had a small asteroid. So you can kind of get maybe a rough idea about the size of the failed asteroid that broke apart that these iron meteorites come from. So by studying meteorites that fall here on Earth, we can get a sense of what was going on in the asteroid belt at one time or another, what sort of size of asteroids these objects came from, had they been heated. These ones have been heated, this one hasn't so much, and even if they've come from planets proper, like Mars. And we also get meteorites from the moon. So the OSIRIS-REx mission, how does it fit into this? We've talked a little bit about security, we've talked a little about meteorites. So the OSIRIS-REx mission's goal is to study these things and more. So one of the goals of the OREX mission, call it OREX because it is a mouthful of an acronym, is studying the origin of our solar system and the origin of asteroids, looking at spectral interpretation, looking at this asteroid through a variety of wavelengths of light, looking at resource identification. There's been a lot of talk about asteroid mining in the news lately. Security, what happens if these asteroids were to come close to Earth? How could we possibly deflect one, and could we do it effectively? And then finally, exploring the surface of the asteroid. This acronym is a mouthful, and to get a mission funded, you have to propose it several times to NASA. And they originally proposed this mission as just OSIRIS, Origin, Spectral Interpretation, Research, Resource Identification, Security. And so they proposed it a couple of times to NASA at a cost cap of maybe a couple $100 million. And then eventually there was a call for more expensive missions. So they said, all right, we're gonna apply again for more money from NASA, but we want to make it sound more robust. We want this mission to sound more stalwart. I know, we'll add Rex to the end. They tacked on the Rex. They figured out this Regolith Explorer thing, and we'll explain. I'll talk about Regolith Exploring in just a bit. So if this acronym, if you find it difficult or annoying, it took me about 2 years to memorize what it stood for, so don't feel too bad. And I think there have been a number of press conferences where people have defended this acronym. So origins. We've talked about these primitive meteorites that have remained unchanged since the origin of the solar system. And so this meteorite, we have a little scale bar over here. So this is one called Allende. Allende fell in Mexico in about 1968, right before the Apollo moon missions were happening. And so NASA had been helping people build all these laboratories to study meteorites, or to study samples from the moon, to study the various elemental isotopes in them, to study the minerals. And so suddenly this meteorite falls from the sky, and it has a very primitive, a very unchanged composition since the beginning of the solar system. And fortunately, there are all these laboratories that have just been set up to study rocks from other worlds. So Allende fell at this fantastic time when we were just building capacity in the 1960s to study things like this. And the cool thing about Allende is it has these little white things. And these white things are made out of calcium and aluminum, and they were the first things to condense in the solar system 4.6 billion years ago. These little white things are older than the Earth. So if you ever get a chance to hold a piece of Allende, maybe Brian has a piece of it. I got a piece of it at a conference 9 years ago. It's really cool just to know that this predates the Earth, and it's what the Earth is built out of. So OSIRIS-REx is going to visit an asteroid that we think has a very similar composition to a meteorite like Allende that has remained unchanged since the origin of the solar system. But what OSIRIS-REx will improve on over just a meteorite like Allende is that the meteorite has the material, the material from the asteroid will have been out there in space. It won't have fallen through the atmosphere. It won't have been heated as much, perhaps. And so by going to the asteroid, by going to the source of this material, hopefully we'll be getting a sample from something that's remained unchanged for 4.6 billion years, even more so than anything that we have here on Earth. Spectral interpretation. So we have a couple of physics students here, and we have a couple of astronomers. So what spectral interpretation is taking light and shining it through a prism and looking at it at the variety of wavelengths that you get when you split light through a prism. And so there's a number of instruments on board. There's 2 instruments on board that look at the asteroid in different wavelengths than we would see with our eye. So OTES, what it will do is it's like an infrared camera that looks at the surface of the asteroid, of Bennu, but it looks at it at a variety of wavelengths. And so you can kind of see here that they think Bennu might look like this in the thermal. And so if you're looking at Bennu, if you're looking at a heat map of Bennu, how it reflects infrared light, you expect to find that some particles will heat up and cool down faster than other particles based on the particle size. And so by sending these spectrometers to Bennu, we're hoping to understand not only what parts of the surface are hotter and cooler, but also you can get the sizes of particles on the surface just by looking at what sort of heat, which is pretty neat. So OTES has been built at Arizona State University up the road in Phoenix. I got to see it last January before they shipped, and I think it was the first instrument ready to go on the spacecraft, which was pretty cool. Another one of the spectral interpretation instruments is called OVIRS, which is the OSIRIS-REx visible in infrared. It's another spectrometer. And so this is again going to be looking for organic material on the surface of Bennu, looking for long chain molecules that might have been precursors to life here on Earth. So combining information from these 2 different instruments, you can find out a lot about the size of particles on the surface. Are there a lot of big particles? Are there small particles? Is there a mix? And then also start looking for various organic materials. Is there dark gunk on the surface of Bennu? How did it get there? Where could it have come from? And then finally, resource identification. Someone here mentioned asteroid mining earlier. Great. there are now 2 asteroid mining companies. There's Planetary Resources and there's Deep Space Industries. When you have one asteroid mining company, you think those guys are maybe a little weird, they're maybe a little out there, maybe they're a little batty. When you have 2 asteroid mining companies, you suddenly have an industry and people start taking you seriously. And the Grand Duchy of Luxembourg starts writing laws to help space asteroid mining happen. And so a lot of people think that asteroid mining will be looking for platinum group elements, platinum, titanium, things like that. But right now, the cost of these elements on Earth aren't high enough to really justify the infrastructure of going out into space from an asteroid and bringing it back. Sure, some of these asteroids probably have billions of dollars worth of platinum or titanium on them, but it just isn't cost effective to try to get that material back down to terra firma. So the goal right now for a lot of asteroid mining is to be getting water out of the surfaces of these asteroids. And so an asteroid like Bennu, it might have 10% of the rocks on its surface. It could have water in those minerals, locked up in those minerals in hydrated minerals. So you can get water out of these asteroids perhaps, and you could turn that into drinking water for astronauts. You can split it into hydrogen and oxygen and get rocket fuel for your spacecraft. You can even use that water for shielding to protect you from cosmic rays that would damage you and your facilities and your computers out there in space. However, in addition to water, these asteroids also have a ton of sulfur. They have a ton of cadmium, arsenic, selenium, tellurium, antimony, just really, and mercury, really nasty elements that you don't want to spend time with. And so if you're trying to vaporize water, you're going to have really high concentrations of sulfur and mercury in that water. So don't drink the asteroid water yet until someone has figured out how to purify that water so that you don't poison yourself. So there's some chemists who are working on these problems at some of the space development corporations, trying to come up with filtration schemes for water vapor so you can get the sulfur out of it so you don't kill future astronauts. But the idea behind resource identification is that you could have a more sustainable presence in space. The Apollo missions were just sort of a series of one-night stands on the moon. The International Space Station has to be constantly resupplied from Earth. But if you could get a way to have water in space, suddenly you've solved your rocket fuel problem, you've solved your drinking water problem, and you've solved your shielding problem. So if you can bring in situ resources, you're set. Security. So I like this image a lot. I think it's pretty funny. But the idea is that if you have an asteroid that's going to come too close to Earth, what are you going to do? You can't just, roll up to it and say, hey, could you get lost? Because an asteroid is just a dumb rock. It's not sentient at all. So you just can't ask it nicely to go away. We've all seen Armageddon. We've all seen Deep Impact. And so there's this idea that you could put a kinetic impactor, or in less polite company, a bomb on an asteroid and blow it up. But then instead of having one asteroid, then you have a bunch of asteroids. And so a lot of these bodies, we think they're not actually one solid chunk. We think they're a whole bunch of little particles stuck together, that they're kind of like a mountain of gravel, right? They're just sort of a gravitational aggregate in polite company, or a rubble pile. They're not really stuck together very well. They're not perfectly spherical. So if you try to blow it up, you might not have much luck. So maybe you need to sort of gently nudge it with a spacecraft. Maybe you need to put a massive spacecraft next to the asteroid to change its orbit. Maybe you need to paint half of it white. The spacecraft is painting this asteroid white in this image. Imagine you're in a parking lot on a hot day in Arizona and you're walking barefoot. Are you going to walk on the white paint, or are you going to walk on the dark asphalt? You're going to walk on the white paint, so it reflects light differently. And so you can actually get asteroids to reflect, if you can get light to reflect differently on the asteroid, it can actually cause the asteroid to change how it spins, and it will even change its orbit based on just sunlight reflecting off an asteroid. So if you can understand what the asteroid is made of, is it one solid chunk, is it a bunch of big chunks, or is it a whole bunch of little chunks? And then finally, how does it respond to sunlight? Does it heat up and cool down very quickly or very slowly? So if you were going to paint half of it white or cover half of it in Mylar, how would that affect the orbit? And then finally, security again. So three and a half years ago in February in Russia, this meteorite exploded over a town called Chelyabinsk. And so this is sort of the highlight reel. I don't know if one can hear the sound. But you can definitely see the effects of the shockwave of this meteorite exploding in the air above Russia. And so all these Russians, it's early in the morning, everyone's commuting to work, and everyone runs outside. And then they were like, what's this explosion? What's this light? And then all of a sudden the shockwave hits them. And you can see all these windows breaking. It was a really lousy day. Also, it was really cold there, probably minus 30 Celsius, so pretty chilly, suddenly blown out. So you have a problem when that happens. So even though this meteorite explosion didn't kill anyone, it still broke thousands of acres of glass. And here is my little chunk of Chelyabinsk. This is from Russia with love. And the asteroid that exploded in the air was only 60 meters. And so it didn't kill anyone, but it still caused a lot of problems. So if you can find these asteroids before they find us, you can hopefully mitigate a lot of problems. See if I can. There we go. So finally, regolith explorer. What is a regolith? A regolith is just the asteroid term for the dirt on an asteroid. And so regolith it's all the rocks, it's the pebbles, it's the grains of sort of asteroid sand. This is an image of asteroid Itokawa that was visited by a Japanese spacecraft a number of years ago. And you can see that it's got some big boulders on the surface that are barely sticking on, and it's got also some really fine material on the surface, so it's got the sand. So we don't really know a lot about regolith on asteroids. The Japanese have visited one asteroid, and it's this one that we think is really stony, and we think it's been changed a lot in the last 4.6 billion years. Maybe it's been heated up, it's been ground down, a lot of things have happened. But we don't really know very well how the grains on these asteroids stick to each other. It could be that if you're an astronaut and if you landed on this asteroid, you would actually sink up to your waist in pebbles. And then if you could get out of the pebbles somehow, you would be covered in pebbles like you'd crawled into a container of powdered sugar or flour. That we think that the cohesion, how these grains stick to each other and stick to other things, could be very similar to how powders work here on Earth, except you'd be covered in pebbles as an astronaut, and you would be sad because then you couldn't get them all off before you got in your spacecraft, or then you'd have pebbles all across your spacecraft. So we don't really know exactly how the regolith on these bodies behaves, and so that's why we're sending a spacecraft. All right, so we've done origins, spectral interpretation, resource identification, security, regolith explorer. Whew, that's an acronym. So September 8th of this year, just a month ago, wow, was launch. And so a lot of us went down to Cape Canaveral, which just missed being completely destroyed by a hurricane. And we got to go to launch. So let's see if I can get unmuted. Nope. Sorry. Let's try. Can you hear this? This is launch.
Yeah, we can't hear that. I don't know. I'm not sure why we wouldn't be able to hear that. Is the volume up on the computer there, Sonia? Okay, we can hear now, okay?
All right, no feedback this time. All right, so launch was great fun. Launch was perfect. Launches of spacecraft are almost never perfect. There's always some sort of delay. There's always, maybe it needs to be scrubbed for the next day. And it launched within 180 milliseconds of the launch window opening. It was amazing. The rocket just went up, and that was it. And it deployed its solar panels. The spacecraft is happily ticking away. It's taking calibration data. All the instruments are working great. Everyone is super stoked. So launch is a huge relief, because then everyone has a job for the next 7 years until the spacecraft comes back with its sample, and then various other people will be analyzing the sample in labs. But why this asteroid? Why is OSIRIS-REx going to this asteroid in particular? Its name is Bennu. It's named after an Egyptian mythological bird that has to do with death and rebirth. And since the asteroid Bennu itself is potentially hazardous, it could come hit the Earth in 150 years. And since it is associated with the origin of the solar system, people thought that Bennu was an appropriate name. So of the 500,000 or so asteroids that are out there, we know of about 7,000, almost 14,000 today, that are near Earth. And so of those 7,000, there are about 200 that had orbits where you could get to them with a spacecraft, sample the asteroid, and then return that material to Earth. And of those 200, about 26 are large enough that you could actually put a spacecraft nearby and have a variety of sites to select where you would get material from the asteroid for sampling. And then of those 26, 5 appear to be carbon rich when you look at them from Earth if you take spectra of them. So we think they're very dark. We think they've remained unchanged for the last 4.6 billion years. We won't really know for sure until we get there. And then of those 5 that are carbon rich, that are large enough, that have good orbits, that are near Earth, only one had a shape model. Only one of them we knew what it looked like. So how do you get a shape model of an asteroid? You can actually go online, you can download the shape file for this, and you can 3D print this at home. I don't know if your library has a 3D printer, but you can make your own asteroid Bennu. So to get a shape model of an asteroid, you actually have to leave the continental US and you have to go to Puerto Rico, which is not a bad deal. And in Puerto Rico, on sort of the central northwest coast, is a giant radio telescope. And so radio telescopes can do really cool things, including doing radar of asteroids. So a lot of people are familiar with Arecibo Observatory if you've watched GoldenEye 007, if you've watched Contact, you've seen, if you've played GoldenEye on your N64, I think a few of you are familiar with Slitty. Arecibo not only is home to Bond supervillains and Jodie Foster's character, it is also a place where you can do radar. And radar works by transmitting radio waves from the observatory out into space, and then they bounce off the asteroid, and they come back to the radio telescope, and you collect them. And so radio is very different than looking through a telescope like the ones you'll be looking through tonight, because radar creates its own radio waves. You don't just look at light that's reflected from the sun passively, you actually actively create your own signal. And then when you get it back, you can actually very precisely study the surface of an asteroid. And so asteroid radar is a slightly separate talk, and sometime, and I will talk about it for hours, and it's great. But you can actually get a shape model of an asteroid by studying it with radar. And so you send little radio waves to the asteroid, and you get a ping back, and so you can get the surface of an asteroid very precisely to maybe 10 meters, that's 30 feet. So we have less than 30-foot resolution on this asteroid. We know how big it is. We know that it sort of has this equatorial ridge. We know it has a boulder. We don't really know if it's in the north or the southern hemisphere, but we'll find that out in 2018 when the spacecraft arrives at the asteroid. And so right now we know that this asteroid is about 500 meters across. It's pretty big. It's bigger than the stadium, what is it, Albertson Stadium you have there at Boise State. This thing is large. It is not small. It's the size of a respectable mountain down here in Tucson. And so here for scale are a couple of buildings, including Bennu. So you have Bennu coming in at about 510 meters from north to south. You have the Empire State Building and the Eiffel Tower. So we know how large this asteroid is. We know what it's shaped like. We know that it takes about 4.5 hours to rotate. We know a lot of useful information about this asteroid, so that when we send the spacecraft there, we don't have any unpleasant surprises. The Europeans recently sent a spacecraft that arrived 2 years ago at a comet, and they just crashed it onto the comet last week, a week ago today. And so they were, when they designed the mission and when they launched, they expected the comet to look sort of like a squishy stress ball. And when they rolled up to the comet, Comet Churyumov-Gerasimenko, the Rosetta spacecraft found that it looked more like a rubber duck. So everything that the mission had been designed to do was designed for the squishy stress ball shape, and instead they got a rubber duck. And so that caused some problems. So if you know what your asteroid looks like ahead of time, you have fewer problems when your spacecraft gets there. You can more efficiently design your images, your what sort of images you'll take, your instruments, and even how you're going to sample the asteroid. So the final instrument that I think is really cool to talk about on the OSIRIS-REx spacecraft is the TAGSAM. This is the touch and go sample mechanism. And so most people think, oh, I'm going to go to an asteroid and I'm going to scoop material off the asteroid and it'll be great. But except for the fact that this asteroid is just it's a pile of gravel. It's not really cohesive and it doesn't have a lot of gravity. It's got 10 micro Gs. It has practically no gravity compared to Earth, so a scoop won't work. So they actually came up with this touch and go sample mechanism sampling head, which is like combining an engine air filter from a car with a compressed gas canister that shoots out nitrogen gas. So let's take a look at the touch and go sample mechanism. Which I think I don't think this one has any sound, but you can see sort of how this mechanism works by shooting out gas, and then material from the asteroid is actually sucked into the sampler head. And so they tested it on NASA's Vomit Comet, which is this airplane that flies in parabolas so you can get microgravity simulated, so you can test a mechanism like this to see if it would work in microgravity. And it actually does. So here is the sample being tucked into the sampler head and being stowed so that it can be eventually returned to Earth, and it will return to Earth in 2023. So what exactly is OSIRIS-REx going to find at Bennu? Well, we're hoping to find a lot of information about an asteroid that has remained hopefully unchanged in 4.6 billion years. We're hoping that it'll have a lot of organic material on it, maybe. Maybe it'll have a lot of those calcium aluminum inclusions that haven't been heated up or melted down in 4.6 billion years. Maybe it'll have some big boulders on it. Maybe it'll be a whole pile of rubble. Maybe it'll be Maybe it'll be a couple of big chunks. Maybe it'll have more boulders. Maybe it'll be such an interesting object that we'll send another spacecraft to visit it at some point and bring home an even larger sample from it. But there's a lot of exciting stuff that can happen. We're going to learn a lot about an object that may hit Earth at some point that will hopefully be invaluable information should we need to deflect this asteroid from hitting us. And the touch and go sample mechanism is something that's never been tried before. So it's going to be really exciting to watch that work and watch the sample come back to Earth in 2023. Hopefully I will be out of school by then. If I'm not, we'll have other problems. And so finally, there's one last OSIRIS-REx video I'd like to show. This one's only a couple minutes. And then after that, I will take questions.
NASA's OSIRIS-REx spacecraft is heading to asteroid Bennu and back. The OSIRIS-REx mission goal is to study near-Earth asteroid Bennu and return a sample to Earth. OSIRIS-REx's launch window opened September 8, 2016 from Space Launch Complex 41 at Cape Canaveral, Florida. The spacecraft, nestled inside a Centaur upper stage, launches on an Atlas V rocket with a single solid rocket booster. The rocket's first stage separates, and then the Centaur upper stage fires. The bearings separate from the rocket, and the OSIRIS-REx spacecraft releases from the Centaur upper stage. Angled toward the sun, the spacecraft deploys its solar arrays. Now traveling over 25,000 miles per hour, OSIRIS-REx escapes Earth's gravity and begins its cruise toward asteroid Bennu. After 23 months, the spacecraft arrives at asteroid Bennu in August 2018. With its suite of observational instruments, OSIRIS-REx orbits the asteroid, studying its characteristics and mapping its surface. After 4 phases of survey observations, OSIRIS-REx begins preparations to collect the sample. In July 2020, after months of rehearsals and study, the spacecraft approaches for sample collection. It slowly descends to Bennu's surface at less than a quarter mile per hour. With an outstretched arm, OSIRIS-REx briefly touches the surface. The touch-and-go sample acquisition mechanism, TAGSAM, blows high-pressure nitrogen gas into the surface rocks and dust, sending loose asteroid material up into the TAGSAM head. OSIRIS-REx backs away from Bennu and stows the sample in a capsule for its journey to Earth. In March 2021, the window opens for OSIRIS-REx to depart Bennu. The spacecraft returns to Earth September 24, 2023, and jettisons the sample return capsule. The spacecraft leaves Earth, and the return capsule enters the Earth's atmosphere at over 27,000 miles per hour, protected by a heat shield. A couple miles above the surface, a parachute deploys. And the capsule lands softly in the Utah desert. Bennu's secrets can now be investigated for decades to come.
So all these videos are online, and I'm going to put up the links at the end. So I got to go see the spacecraft in July before it got boxed up and put in the fairing, which was sort of exciting. Had to put on this extreme bunny suit and had to have a beard protector, even though I don't have a beard, and had to tape gloves around my wrists, and it was quite an experience. So it was really cool to see the spacecraft before it got launched, and then to see it launch, and hopefully in 7 years there'll be more science to be done with the material that comes back. So that's all I have. If you are on social media, they're even on Google Plus, and there's even a blog that the principal investigator Dante Loretta maintains. So if you want to follow OSIRIS-REx, there's all these animations are online. The mission has a YouTube channel. Goddard Space Flight Center from NASA, they have a lot of videos as well. There's a lot of content tagged with to Bennu and back, especially from launch. So with that, I am happy to take your questions. Thank you very much.
Okay, so let's do this. Karen, when you come up, I'm going to hit, Sonia, you can hear us, right?
Yes.
Good. Okay, so Karen's going to bring a mic around for folks, and we'll try to get them on camera if possible. You need to speak way down into the mic to make sure that she can hear, because the mic that she's listening to is way down here, okay? Does that make sense? All right, so who has questions? All of you have questions, I'm sure. Yeah, right here.
Yeah, can you hear me?
Yeah, I can hear you great.
Okay, cool. So you mentioned during the resource part of your presentation that that we could be using things like water for shielding.
Yeah.
Like cosmic rays. Can you explain how that's used?
Sure. So there are these nasty cosmic rays out there in space, and cosmic rays will hit your DNA and they will fry your DNA. And if you're exposed to too much radiation out there in space, you can get quite ill.
Right.
It's unpleasant. Also, if you are electronics, like in a computer or pretty much anything that you would have out there controlling your spacecraft, electronics can fry as well from cosmic rays. It's not a huge problem here on Earth, but occasionally you have a cosmic ray hit the RAM in your computer and it will do a calculation weirdly. Okay. So the more you can be shielded, and water absorbs cosmic rays pretty well. Really, the best shielding is dirt. So if you can get a nice layer of regolith from your asteroid or moon or Mars and hunker down under that nice layer of dirt, pretty happy. But if you can't do dirt, you could do water.
Interesting. Yeah, because I've heard using like gold filament as a means of insulation from cosmic rays, but I didn't know that you could use water in that same sense.
Yeah, if you have enough water, you can do that. Neil Stevenson talks a little bit about this in his book, 7 Eves, which is some fun sci-fi about how do you get humans surviving in space. But I digress.
Okay.
But water is cool because you can also drink it if you're using it for shielding.
Other questions? Right here. Oh, it's backwards on the screen now.
Can you hear me?
Can you hear us, Sonia?
Yeah.
All right. Do you have any advice for new students who want to get to where you are?
Don't do what I did. You know, pass your classes, do okay, do research during the summers if you can, do research during the school years if you can, network, talk to people, go to meetings, print business cards, read papers, be interested, and don't be afraid to take some time and actually get a job in the field if you're not sure you want to go to grad school, or if grad school is being a terrible endeavor. There are tons of jobs out there. They're not tons of jobs, but there are jobs. Space Telescope, they run Hubble, and they're going to be running the James Webb Telescope. They often have entry-level jobs for recent grads, doing support for a lot of astronomical image, helping astronomers take images with Hubble. There's a lab in Colorado that will hire people with that experience, and we just had a job that closed yesterday actually doing uplink for the HiRISE camera that's on a spacecraft in orbit around Mars. And that, I don't even think you needed a college degree for that job. So there are a lot of opportunities out there to work in astronomy, work in planetary science without going to grad school, so you can decide whether or not it's something you want to do and get paid better than a grad student would. And be persistent. I am maybe too stubborn for my own good, and I stay with things longer than I perhaps should, and that's probably why I'm here.
We also have Physics and Astronomy Club here at Boise State. We, of course, have a physics major. There's active research programs in astronomy and planetary science here at Boise State. So that's another thing to try what you're interested in. Right?
Yeah, and there's a number of research programs throughout the summer in a variety of places. There's actually one at Arecibo Observatory. The RU program there is great. We actually had there was a student in the group who came back 2 summers in a row because everyone loved him and he loved the place too. So there are opportunities out there, and if you don't want to go out of the country, there's probably some in Idaho, there's probably some in other states. There's, I think even one of the observatories in Chile lets you come down there and work at the observatory there. And there's generally telescope operator jobs too, that if you think staying up all night for weeks at a time, helping people look at stars and galaxies and planets is a sweet deal, those jobs exist as well.
How many samples are you planning to take from the field?
Sorry, you're gonna have to put the microphone.
I was asking how many samples you are planning to take.
They're gonna bring, it's only gonna sample once, because as soon as they have a sample, they're done. They're gonna go back to a safe distance from the asteroid and they're gonna come back to Earth, because the longer they hang around, the riskier it is that something will go wrong. So they're gonna bring back up to about 4.5 pounds of material. I think that's 70 grams.
Other questions? Way over here.
Will you know at the time that you've got a sample?
Did you hear that, Sandy?
Yeah, so they're going to check it in a couple of ways. One is there's actually a camera mounted near the sample canister to check that they've got something in the sample, that the sampler head is in there. And then what they're going to do, for all you physics and astronomy people, is they're going to rotate the spacecraft and they're going to see how the angular momentum has changed. And if the angular momentum has changed consistent with having sample on board, then they know they have sample. And then they're going to peace out and head back to Earth. Physics.
Yeah, in the back.
You think those problem sets are a waste of time. A waste of time.
Question here in the blue. Hang on a second.
All right, so my question is, you said it's gonna have a couple months there to circle the asteroid and get some information there. Is it? Are we gonna be able to get some great high-res pictures, or is that capability on the side?
So they get to the spacecraft in 2018 and they leave in 2021. So there's going to be 3 years of images there, and they're going to be great photos. So if you like piles of rocks in space, man, this is it. They're going to be amazing high resolution images. They're going to be counting rocks. If you like doing citizen science, and if you think nothing would be more fun than going on the internet and counting rocks on an asteroid, well, you're in luck, because you can do that. They're going to be doing a variety of having humans counting rocks. They're going to be hiring undergrads. They're going to be having citizen scientists do it online, and they're going to be using both undergrads and other humans to train the algorithms to count rocks on their own. So eventually the computers will do it, but before that, there's going to have to be some human intervention to do some training. So yeah, look forward to high resolution images and, you know, desktop backgrounds galore.
How much water could you conceivably find on an asteroid the size of that might be hidden in like water?
So you know, it's 10% water by mass, maybe. So, you know, if you've got 100 kilograms of material, you might even have 10 kilograms of water in there. Maybe that would be pretty optimistic and pretty cool.
Other questions?
And if you have other questions, you can bug me on Twitter. I'm there. My Twitter username is Sandy. I have the website sandy.com. You can find me those places. I'm infinitely Googleable.
Great. Let's thank Sandy one more time.
Thank you all so much. This was great fun.
And I'm going to post the video of this presentation on my website, so you can watch this again and again and again if you like. Thanks a lot, Sandy.
Thank you, Brian. Have fun looking at stars tonight.
Yeah, perfect.